I'll start going over the questions for levels 3 and 4. So, level 3. Given that there are 24 primes between 3 and 100 inclusive, how many ordered pairs P and A are there such that P is prime and 3 is less than or equal to P and is less than 100, and A is between 1 and P, and the sum A plus A squared all the way to A to the power of P minus 2 factorial is not divisible by P. And so, first of all, we can consider the case when A is equal to 1. And in this case, the sum is simply just equal to P minus 2 factorial. And clearly, we can see that P never divides P minus 2 factorial. And so we know that there are 24 primes between 3 and 100. So there are 24 solutions of the form P and 1. And so next up, if A is not equal to 1, then if A is not equal to 1, then the sum is simply just equal to simply just A plus A squared plus A cubed all the way to A to the power of P minus 2 factorial. And this is simply just A times A to the power of P minus 2 factorial minus 1 divided by A minus 1. And the reason is because we can factor out a factor of A, and then this is simply just adding from 1 to A all the way to A to the power of P minus 2 factorial minus 1. And so this, we can just rewrite this as A over A minus 1 times A to the power of P minus 2 factorial minus 1. And so now we know that A is between 1 and P, and A cannot equal either 1 or P. And so that means that A over A minus 1 does not, that means that A over A minus 1 does not affect divisibility by P. And so that means that we can effectively ignore this factor. And so what we focus on is just A to the power of P minus 2 factorial minus 1. And so the first case is if P equals 3. And if P equals 3, then A to the power of P minus 2 factorial minus 1 is simply just A to the 1 factorial minus 1 or A minus 1. And so the only possible value of A is if A equals 2. And we can see that the combination of 3, 2 works. And so next up we have P equals 5. And so in this case, we can see that this is equal to A over A minus 1 times A to the power of 6 minus 1. And so we know that by Fermat's Little theorem, A to the 6 is congruent to A squared mod 5. And so this is equal to A over A minus 1 times A squared minus 1. And we can simplify this into just A times A plus 1. And so next, if we test A equals 2, 3, or 4, then we can see that these two 2, and 3 work, but 4 fails. And so that means that 5, 2 and 5, 3 are both solutions. And so finally, otherwise we have that P is greater than 5. And so if P is greater than 5, then we can see that P minus 2 is greater than P minus 1 divided by 2. And so and so then what that means is that, and we also have that 2 is not equal to P minus 1 over 2. And so that means that P minus 1 is always composite. And so also it's always divisible by 2. And so that means that there's always some other factor of P minus 1 now that's not 1 or 2 for itself. And so that means that P minus 1 can always divide P minus 2 factorial, as long as P is greater than 5. And so that means that by Fermat's theorem, a to the power of P minus 2 factorial is congruent to a to the power of P minus 1. A to the power of P minus 2 factorial minus 1 is congruent to a to the power of P minus 1 minus 1, or 1 mod P. Oh, not 1. 0. And so that means that this case always fails. And so we have that the total number of sums is simply just 24. The total number of solutions is just 24 plus 1 plus 2. And this is equal to 27. And so the answer is 27. And so now on to level 4. So level 4. Find all functions f such that for all real numbers x and y, we have that f of x plus xy times f of x minus 3y plus f of y times f plus xy times f of 3x minus y is equal to the square of f of x plus y. And so if we know, so first of all, we can substitute x equals y equals 0. And so that from this, we can directly tell that f of 0 is equal to 0. And so now we can set x equals 0. And what we get from this is that f of y times f of negative y is equal to f of y times f of negative y is equal to f of y squared. And so if f of y is not equal to 0, then we can see that this means that f of y is equal to f of negative y. And so that means that, and so now we can substitute y equals negative t. And what that means is that if f of t is equal to 0, then we also have that f of negative t is equal to 0 for t in R. And so next we can see that let's set x is equal to 3y. And if we do this, then we can find that f of y plus 3y squared times, excuse me for a second. So f of y plus 3y squared times f of 8y is equal to f of 4y squared. And so now if we substitute y equals t over 8, then what we get is that if f of t is equal to 0, then we also have that f of t over 2 is equal to 0 for t for real t. Yeah. So now next we can set y equal negative x. And so in this case we have that f of 4x times f of x plus f of negative x minus 2x squared is equal to 0. And so as long as f of x is not equal to 0, then we can see from this. As long as this is true, then we can see from this that f of 4x is not equal to 0 as well. And so that means that 2x squared equals f of x plus f of negative x. And using this, we can see that this is equal to simply 2f of x. And so what this means is that we can see that either f of x equals 0 or f of x equals x squared. And so now we want to show that there are no other solutions other than these two. And so we can see from here that we know that f of y plus 3y squared is not equal to 0. And so we can see that as long as f of t is equal to 0, then we also must have that f of 2t is equal to 0. And this is done by the substitution y equals t over 4. Y equals t. And so, in addition, if f of a equals f of b equals 0, then we can see that we can pick xy such that x minus 3y is equal to a, and 3x minus y is equal to b. And so we can see that x plus y must then be equal to b minus a over 2. And so because of this, we can see that this means, and if we plug in x equals y, then we see that f of b minus a over 2 is equal to 0. And from this, we can see that this implies that f of b minus a is equal to 0. And so now we can assume that as long as f is not congruent to 0, and we also have that f of t is equal to 0, and now we want to assume that t is not equal to 0. And so we want to show that this is a contradiction. We want to show that this is false, and so that would mean that f of t equals 0 if and only if f of t is also 0. And assuming that f is not just a 0 function. And so now we can pick xy such that x plus y is equal to t and f of x is not equal to 0. And so we can see that f of y is also not equal to 0 because we know that x plus y minus y is equal to x. And so that means that if f of y is equal to 0, then by this, we can see that f of x would also equal 0, which is a contradiction. And so now you can also see that f of x minus 3y is also, sorry, we can also see that f of 3x minus y is also not equal to 0. And this is because actually, yeah, this should be x minus 3y. If f of x minus 3y is not equal to 0, and so we can show this because x plus y minus x minus 3y is equal to 4x. And so that means that f of x minus 3y is equal to 0. And so that means that if this is true, then that implies that f of 4x, sorry, f of 4y is equal to 0. So that implies that f of y is equal to 0. And once again, this is false because of the line of arguments. And so the final case is when f of 3x minus y is not equal to 0. And similarly, we can once again use contradiction. And the contradiction works because f of 3x minus y equals 0 implies that f of y minus 3x is equal to 0. And so since we know that x plus y minus 3x is equal to 4x, this means that f of 3x minus y is equal to 0 would imply that f of 4x is equal to 0. And so that would mean that f of x is equal to 0. And so once again, we can see that this is a contradiction. And so that what this implies now is that f of y is equal to y squared, f of x minus 3y is equal to x minus 3y squared, and f of 3x minus y is equal to 3x minus y squared, because of what we've already shown up here. And we will also assume that this is not true. And so the way this works, because we've already shown that this works for all reals, but we still don't know if this works for all if these are all possible functions f. And so now we can plug this into the equation. And so that would give that x squared plus xy times x minus 3y squared plus y squared plus xy times 3x minus y squared is equal to 0. And we can factor this left-hand side as simply just x plus y to the power of 4, and this equals 0. But at the same time, this would imply that x plus y is equal to 0. But we also define that t is equal to x plus y, and it's not equal to 0. And so this is a contradiction. And so that means that the only solutions are f of x equals 0 and f of x equals x squared. And now we can, if we want, we can plug them into our original equation up here, this equation, and we can see that this is both of these hold true. And so that's it for the level 3 and 4 questions. And so thank you for listening.